Thanks, Joel. And good afternoon, ladies and gentlemen. I understand my job is to take something that you probably haven't learned much or anything about at school, which I think you should learn something about, and teach you some aspects of that. And Joel, you mentioned I was a director of PDAC. One of the things I've noticed in being a director for PDAC is that there seem to be two kinds of directors, geologists and lawyers. And the lawyers, they're paid, they speak as if they're paid by the word. So you might be, you probably have all seen any presentation like this that a company gives. There's always a whole page of tiny letters that you have to read. Two geologists took it on themselves to translate that into English, and this was their result. And I think it shows that geologists are in many ways much more admirable at handling the English language than lawyers. And the topics that you might not have learned about but should do, as the title of the presentation says, involve net smelter returns. And I'd like to teach you about how to answer three questions. And here's the first one. You've got two geologists in the Northern Cordillera. You're looking for deposits of silver. And I'll go over to them and I'll say, which would you rather find? A zinc-silver deposit or a lead-silver deposit? And the typical answer I give to that is something like, well, this morning the price of zinc on the London Metal Exchange was $1.17 a pound. The price of lead was 99 cents a pound. So I'd rather find a zinc-silver deposit, right? And it's good to learn why that's the wrong answer. For the second question, it's that one. If you have these assays, how can you tell which of these set of assays, 86F or 86C, is the better? And we'll look at that. And the third question addresses First Quantum Minerals, Inc., which is the world's largest pure copper play listed on a stock market. And First Quantum's financial statements present the revenues from the company's operations in a format like this. And if you were to try to replicate these revenue numbers, what you might do is to go elsewhere in this First Quantum financial statement, and you find the part that tells you how much copper Chile produced in 2016, and you multiply that number by the average price of copper in 2016, then do the same for the zinc produced by Chile, then the same for the gold and the silver produced by Chile. And you add up all those revenues from each of the commodities, and you get the mine's total revenues. And the number you get for Chile's revenues on that basis will be about $165 million. But you can see that First Quantum has reported that number at $110 million. Why the discrepancy? So my three questions is which is worth more, zinc silver ore or lead silver ore, and why is the answer not intuitively apparent? Secondly, how do you judge the relative values of assays of multi-element mineralization? And thirdly, why does First Quantum, and indeed most polymetallic miners, report apparently low figures for their revenues? And to address these questions, geologists we should really learn to speak managementese. And managementese, well, we all know geologists who have spent or who will spend 2 years of their lives or more learning managementese. And the first thing that you should know about managementese is the vocabulary. When you as geologists speak to other geologists, you talk about the grade of an assay in percent or parts per million. And managementese, you recast those figures into dollars per ton. But to a scientist, dollars per ton are an inherently unstable measure. They change every day. You'd never publish dollar numbers as grades in an academic journal. It's undignified. But I would point out that the use of dollars lets a mine manager know that a stope that was ore last week is full of waste rock this week. As an example, you can bet that if a mill worker were to report a conveyor belt that was torn, this would be translated into dollar terms very quickly. So how do you translate percentage grades into dollars? Some exploration companies, you see their press releases, they do it by calculating the gross values of the metals contained in the mineralization. And this farmer shows you why gross value is not an appropriate measure. In management teas, her revenues are not 60 cents a pound. Her revenues would be what should actually be paid for her sugar beets, which is maybe only 15 cents per pound of contained sugar. So let's go back to those revenue figures for Chiali. Remember that I estimated Chiali's gross revenues at about 165 million, and yet 110 million is what Chiali reported as its contribution to First Quantum's revenues. And that $110 million is what the accountants believe Chiali was actually paid for what Chiali produced. And in management teas, accountants generally define a mine's revenue as the net proceeds from the sale of mineral products from the mine to a smelter, netting out things like, the smelter doesn't pay you for all the metal you deliver to the smelter. And the smelter also, once it's smelted the material, it will send its products off to a refinery, and that costs too. And there are other costs involved in getting the stuff to a smelter: transportation, treatment, marketing, insurance, sampling, and so on. And the number of that gross figure of 165 million minus those costs and deductions I just mentioned is what takes you down to 110 million. And that is another name for this revenue is the net smelter return. Most Canadian mining companies report their revenues as net smelter returns. And for geologists, there are really two things that are useful. Firstly, they give you a common denominator for evaluating polymetallic deposits. And secondly, they give a healthy awareness of factors that could make her project a star or a dog. And another alternative that people sometimes use is to recalculate assays of different metals to equivalent amounts of a single metal. But there's three drawbacks to the copper equivalent or gold equivalent approach. Firstly, converting everything to its copper equivalent assumes that treatment costs and the amounts of metal the smelter takes but doesn't pay for are the same for all metals. They're not. Secondly, once a company has determined this is our set of equivalence factors for calculating copper equivalents or gold equivalents, those factors tend to stay the same for years, even though fluctuations in metal prices happen every day. And thirdly, the calculation of metal equivalents doesn't allow for nasties. Nasties are those substances that reduce the NSR of a truckload of ore. So the copper equivalent of 1% arsenic, for example, the copper equivalent of 1% arsenic is a negative number. You can use NSRs in exploration, in evaluation, and exploitation, but in explaining how to calculate NSRs, it's easiest to consider the exploitation phase. So think of a mine. The ore from the mine is fed into a mill, and the grades of the ore entering the mill are termed the mill heads. It's a geologist's job to make sure those mill heads are high and as expected. Then the metallurgist takes over, crushes, grinds, and treats by various processes the ore to concentrate the valuable minerals, and the resulting products are called concentrates. Think of them as being like sugar beets. They need further processing to get out the good stuff. And the need to crush and grind ore to make concentrates actually brings out one of the many ways in which a geologist can add value to a mining company. Firstly, fine-grained sulfides are worth less than coarse-grained sulfides. And here's why. The point of a mill is to separate different kinds of minerals. So in fine-grained ores, to avoid running through the mill grains of ore that are made up of different minerals, you have to grind the ore really finely, and that uses more energy than coarse grinding. In fact, the world devotes a surprising amount of energy to smashing and grinding minerals. And if a geologist can reduce that energy spend, this is hugely important. And secondly, the processes that separate and concentrate economic minerals work better on coarse mineral grains. And that's why Glencore's huge MacArthur River zinc, lead, silver mine in Australia's Mount Isa district was discovered in 1955 and it sat undeveloped for 40 years while the metallurgists figured out how to address its ultra-fine size, tens of microns and smaller. And that's something in the initial exploration phase you as a geologist can do, recognize this is a very fine-grained ore, this is a very coarse-grained. Now, the most important process in producing concentrates from crushed ore, whether it's lead or zinc or what I've shown here is copper ore, is differential flotation, which that's where you blow bubbles through a mixture of water, pulverized ore, and magical chemicals. And because of their metallic surface properties, most of the economic minerals, in this case it's copper pyrite, will attach themselves to those bubbles, and so the heavy metals are actually floated off the top of this cell, and there's a froth which is skimmed off and dried. Now, recall that mill heads are the grades of metals in the ore that's fed into the mill. One of the calculations that metallurgists do is calculate the mill recovery of each metal, which is the amount of metal that comes out of here and reports to the concentrate and doesn't go out to tailings. And so the recovery to a concentrate is a proportion of the mill heads. So a good number for copper would be better than 90%, for example. But some economic minerals, or potentially economic minerals, don't have metallic surface properties, so they don't float. And when you're exploring, look out for these minerals. Processing them will require special attention. It might be enough to maybe put thumbs down on the project. Now, I understand you have available 2 Excel workbooks in which I've compiled data about the concentrates that could be produced from ores, and also it shows you how to calculate NSRs of mineralization. One of them is copper, lead, zinc. The other is copper, nickel, cobalt mineralization. But in terms of total world production, the 3 most important types of base metal concentrates are copper, lead, and zinc concentrates. And you'll find in the copper, lead, zinc workbook that I've compiled data on 74 copper concentrates, and I found the average recoveries of the mills that produce them is about 82%, and the average grade of the concentrates is about 25% copper. For comparison, stoichiometric chalcopyrite is 34.6% copper, and bornite is 63.3% copper. So bornite is the reason that some concentrates from Highland Valley Copper in British Columbia have graded over 30% copper. And that's a kind of concentrate that smelters are eager to process. The higher the grade, the better for them. Now, after a mine has waved goodbye to its copper concentrates, it expects to get a check. And that check will be based on the price of metal on the London Metal Exchange at the time of delivery, or whatever time is specified in the contract between the miner and the smelter. But that check is going to be reduced by the trucking costs, rail costs, shipping, and any other means of transporting the copper concentrate to a smelter. And so in computing the NSR, the mine's accountants will allow another 2% for the insurance companies cut and marketing agencies cut, and for spillage on route. Some blows off the top of rail cars. And the smelter and the refinery take this concentrate and they levy smelting and refining charges, which are sometimes called TCRCs, treatment charge, refining charge. And recall that smelters and refineries don't pay for all of the metals in the concentrate that you treat. You can send them so much metal, they'll pay for this much. For example, here's how copper smelters determine how much metal they will pay for. Depending on the contract, they will take a deduction of 1 to 4 units, where a unit is 1 percentage point. And in this case, they would pay for only 96% of the copper that you send them in concentrate. Then the smelter charges a fee to smelt the copper that it pays for, which is a good time to point out that there's another fine point here if you're trying to reproduce the numbers yourself, because freight charges are quoted in dollars per wet ton of concentrate, and a ton of concentrate is usually about 7% water, whereas the smelter fee is expressed in dollars per dry ton of concentrate. And finally, there's a fee paid to the refiner. The smelted copper would grade, say, 99.0% copper, and the smelter sends it off to a refinery, which takes it up to a purity of about 99.99%, for which it will charge the miner a fee. These days it's about 7 cents a pound. I should add about a refinery. A lot of the precious metals that are contained in base metal concentrates wind up in the smelted copper, and they are removed at the copper refinery and paid for there. Lead concentrates, you can see in my model I've compiled 46 lead concentrates with the average recoveries of about 72%. The average grades of the lead concentrates about 58%. And for comparison, stoichiometric galena is something like 87% lead. So in concentrates, there's not only sulfide minerals, there's also some quartz and other waste rocks that the smelter doesn't care for. And as with copper concentrates, the NSR for lead is reduced by freight and marketing fees. In determining how much it will pay you for, typically the smelter lead smelter takes a deduction of 3 percentage points. Smelter also charges a fee per ton of dry lead concentrate, and the smelter produces bullion which can grade over 99.99% lead, so there's no separate refining charge for lead. But the smelting fees have until recently been tied to the London Metal Exchange price of lead. So if the price of lead goes up, the smelter fee goes up too, and vice versa. Price participation was abandoned by copper smelters in 2006. Lead smelters have just abandoned it, perhaps permanently. And we move on to the third major kind of concentrate, zinc concentrates. This is the Polaris mine in the Arctic. Average mill recoveries on 72 zinc concentrates are about 76%. The average grade of concentrates is about 54%, and sphalerite usually grades about 64% zinc. Now, the facility that separates zinc metal from zinc concentrates is supposed to be called a zinc reduction plant, not a smelter. If the concentrates grade over 53% zinc, the zinc reduction plant will usually pay the miner about 85% of the zinc contained in the concentrate. But most zinc reduction plants, that's a historic number. 100 years ago, that's all the smelter could recover of what was sent to it. But traditions die hard, so today Teck Resources' Trail, British Columbia facility recovers 98% of the zinc contained in the concentrate center. But it only pays the miner 85% of that, so it gets 13% free metal. And these days, the miner can probably negotiate that 85% payable figure a little higher because the world's zinc reduction plants are running out of feedstock. We need miners, we have too much smelting capacity. And a reduction plant charges a treatment fee per ton of dry zinc. There's no, as with lead, there's no extra refining charge. And also the treatment fees used to go up or down when the price of lead, when the price of zinc went up or down, but rumors are, like copper and perhaps lead, price participation is being abandoned in the zinc business this year. We're not sure yet. And there's an added wrinkle. Zinc reduction plants really don't like to have iron-rich sphalerite. They will penalize a mine that sends an iron-rich sphalerite. So check the colors of your sphalerites. Honey-colored is best. That's the low-iron sphalerites. Bulk concentrates are mentioned in my Excel workbook. The key part of each one is the left-hand sheet tabbed NSR, and at the bottom of each NSR I show you the netbacks, how much you get paid for your ore after milling, smelting, refining, and metal losses. And I found that of all the copper, zinc, lead ores that I've compiled, they give an average NSR, or an average netback, of only 46% of the gross value of the contained metals. But you can override any of these inputs or calculations with your own figures. For example, you might want to look at what happens if metals are recovered only to a bulk lead-zinc concentrate. A bulk lead-zinc concentrate might contain 15 to 20% lead and 20 to 30% zinc. There's some smelters, like mostly the imperial smelting process, in which you send both zinc and lead together to the smelter, and the zinc and the lead come out separately as metal. So the separation is done at the smelter rather than at the mill. But a miner might do this if the mine is small or has very fine grain or is otherwise a difficult mineralogy, but the netbacks are very low to the mine. So in your initial assessment of lead-zinc mineralization using my models, you're probably best to assume no production of bulk concentrates. Now you can do this by entering zeros for all of the inputs in the bulk concentrates part of the workbook, but I must offer that a quirk of my model is that will give you divided by zero errors, so you have to put in inputs like 0.000001 instead of zero. Molybdenum, I looked at 19 molybdenum concentrates. Molybdenum is usually a byproduct of a copper mine, and the copper mine would sell its moly concentrate to a roaster, not a smelter, and the roaster would pay for all of the contained moly, but at a discount. So the free metal it gets is how it pays for itself. Now the roaster typically doesn't pay for any other contained metals, but Ivanhoe certainly expected a credit for rhenium at its Merlin deposit in Australia. We have to wait. The mine's still not in production, so we still don't know if they've been successful in doing that. And the Island Copper Mine in British Columbia leached gold and silver from its moly concentrates before sending them to a roaster. Now, mines don't usually bother leaching concentrates for precious metals. They let the smelter and the smelter and refinery recover them for them. And to look at how much a mine is paid for precious metals in copper, lead, and zinc concentrates, if you go through my workbook, you'll find that a typical copper, gold, silver ore will give you a netback of 61%, whereas a lead, zinc, silver ore will give you only 47%. Which brings to mind that question before, which is worth more, a zinc-silver deposit or a lead-silver deposit? And here's what my model says for material grading 5% zinc and 1 ounce per ton silver. Net back, you get paid for only 44% of the metals that you send to the smelter. So instead of 5% zinc, 1 ounce silver, how about 5% lead? 1 ounce silver, and there's the result from that one. So even though zinc prices, this is using last year's averages, even though zinc prices averaged 94 cents in 2016 and lead prices averaged only 85 cents, zinc silver ore was worth less than lead silver ore. Why? There's several reasons. The first is that silver more commonly reports to a lead concentrate than to a zinc concentrate in a mill. And secondly, smelters are much better at extracting silver from grains of galena than they are at extracting silver from grains of sphalerite. So they pay you more for the silver in galena than the silver in sphalerite. And if you go through my workbooks, you find similarly gold credits are dependent on mineralogy. Inclusions of gold in chalcopyrite are worth more than inclusions of gold in sphalerite. There's one precious metals found in zinc concentrates you might get paid for. Tex Trail British Columbia facility does give you indium credits for some of its suppliers, and Avalon Metals hopes to do something similar with zinc concentrates from its East Kemptville, Nova Scotia mine. Now, I've focused so far mostly on copper, lead, zinc, so I'll make a few comments on the copper, nickel, cobalt workbook. This is a lot more mysterious because most nickel and bulk nickel copper concentrates are smelted by the companies that mine them. And so there's not much trade in nickel concentrates and bulk nickel concentrates, and it's very hard to find out what smelting refining terms are. I've used some good assumptions in the models I presented with you, but you can be sure that in mid-May, when Lundin Mining publishes a technical report on its Eagle East nickel copper project in Michigan, I will be using its descriptions of current smelter contracts to update my nickel model. Another complication is that in copper, lead, zinc ores, the precious metals are generally silver and gold, but in copper, nickel, cobalt ores, the precious metals of interest are silver, gold, and the platinum group. Now, I think that Glencore and Vale in Sudbury produce iridium metal from ores mined in Sudbury, and maybe ruthenium and osmium. I don't know. But it's unlikely that an outside miner shipping ore to be toll smelted in Sudbury would ever get paid for those metals. Rhodium, if you pushed Vale or Glencore really hard, they might pay for it, but almost all of the precious metals credits that are paid to an outside miner come from gold, palladium, and platinum. So let's return to a question I posed earlier. How do you compare these assays? And TPM is the abbreviation that FNX Mining used for total precious metals. And it's entirely composed of palladium and platinum and gold, but they don't give you the breakdown of those metals. And given that the average price of gold was more than double that of palladium last year, it does matter. What you could do is take part of my workbook where I show the average ratios of precious metals in copper, nickel, cobalt ores, and use that as a basis for allocating the revenues of precious metals. And when you do that, you find that both of these come out to be essentially the same number, $176 a ton, $170 a ton. And so far, we've only looked at stuff that a smelter pays for, but we have to remember that a smelter will ding the miner for the nasties it finds. And if you're one of those who are enthusiastic about the future of cobalt and batteries, and you're bullish on cobalt, you should note that geologists who find cobalt usually do so at the dismay of the companies they're working for, because cobalt almost always incurs a penalty, not a credit at the smelter. And both my workbooks will give you some typical smelter terms for the presence of nasties. They can be significant. For example, the former Samatosa copper, silver, gold mine in southeastern British Columbia shipped a concentrate that contained enough antimony and arsenic to halve the size of the chips that the smelter sent back to the mine. And sometimes nasties give geologists a chance to prove their metal. This is the Octedi. It's a porphyry and skarn copper gold mine in Papua New Guinea, and there's as much as 3,000 ppm fluorine in the skarn. But the penalty, the smelter that Octedi sends its copper concentrates to penalizes Octedi if the concentrate contains more than 500 ppm fluorine. So the metallurgists were set to work finding out where is the fluorine. They found it's mostly in talc and phlogopite. The geos then went out and mapped out all the skarn ores rich in talc and phlogopite, so the mill could blend them with porphyry ore that was poor in talc and phlogopite, and that thereby reduced the peak fluorine content of Octedi's concentrates below that critical 500 parts per million level. So in summary, the most important unit of measurement of grade for a geologist is not, or an economic geologist, is not percent or grams per ton, it's the dollar. Dollars are the vocabulary of managementese, and that's a language that all economic geologists should speak if they're interested in getting their views heard by management and the board. And secondly, for many purposes, for example, the comparison of drill hole assays, the grades of polymetallic deposits are best expressed by the net smelter return per ton. Geologists should be very wary of recasting polymetallic assays in the form of copper equivalents or gold equivalents, which imply that the percentages of metals that are payable and the smelting fees are all similar. That is emphatically not the case. And it's also emphatically not the case that all precious metals have the same price. So as a geologist, you should vow never to lump assays of precious metals together as total precious metals. The investor reading that is confused, and rightly so. And thirdly, consulting an NSR model forces a geologist to address a number of factors that might determine whether or not a body of mineralization could become an ore deposit. Some of those factors are determined largely by mineralogy. Now, you can use my Excel models, but they're not plug in and play. To construct an NSR model for an exploration assay or a geometallurgical domain, you'd have to check every line of the NSR tab on the model. And in some cases, the numbers that my model produces will be very rough because the approximations that you've used on smelting fees and payabilities can be very rough. The Excel models, they do give you some regression analyses to make some estimates, but most of all, those Excel models show you what questions you should be asking of metallurgists, of management, and of yourselves. Thank you.